The year is 1945. As Allied forces advance into the heart of Nazi Germany, they discover something unexpected. Hidden in underground factories, concealed in remote mountain facilities, and scattered across captured territories lies a treasure trove of advanced military technology. Rockets that can strike cities hundreds of miles away. Jet aircraft that outpace anything in the Allied arsenal. Submarines designed to operate for months without surfacing. These are not the weapons of a defeated nation, but the technological seeds of the next great conflict. The Cold War did not begin with ideology alone. It was built on the shoulders of German engineers, scientists, and weapons designers whose innovations were divided between two emerging superpowers. This is the story of how Nazi Germany's secret weapons programs shaped the Cold War, and how the race to capture these technologies set the stage for decades of global tension. The final days. Operation Paperclip and Operation Osoaviakhim. As the Third Reich collapsed in the spring of 1945, American and Soviet forces engaged in a different kind of warfare. This was not a battle for territory alone, but a competition for intellectual capital. The United States launched Operation Paperclip, a classified program to identify and recruit German scientists, engineers, and technicians before they fell into Soviet hands. The Soviet Union responded with Operation Osoaviakhim, a more forceful approach that involved the mass deportation of German specialists to the Soviet Union. The prize was substantial. Germany had invested enormous resources into advanced weapons research throughout the war. While the Allies had focused on mass production and incremental improvements to existing designs, Nazi Germany had pursued revolutionary concepts. Some of these projects were impractical or incomplete. Others represented genuine breakthroughs that were years ahead of anything the Allies possessed. The Americans understood what was at stake. General Leslie Groves, who had overseen the Manhattan Project, personally authorized the recruitment of German scientists regardless of their Nazi party affiliations. The moral calculations were simple. Better that these experts work for the United States than for the Soviet Union. Political backgrounds could be sanitized. Scientific knowledge could not be unlearned. The Soviets operated with even less restraint. In October 1946, they executed a coordinated sweep across their occupation zone in Germany, rounding up more than 2,000 specialists and their families. These Germans were transported to the Soviet Union, where they would spend years working on Soviet weapons programs before being allowed to return home. The V-2 rocket. Foundation of the space age. Among all of Nazi Germany's secret weapons, none would prove more influential than the Vogel-Tungswaffe II, or V-2 rocket. Developed under the direction of Wernher von Braun at the Peenemünde Research Facility on Germany's Baltic coast, the V-2 was the world's first long-range ballistic missile. It could carry a 1-ton warhead more than 200 miles, reaching the edge of space before descending on its target at supersonic speed. The V-2 was more than a weapon. It was a technological marvel that combined advanced guidance systems, liquid-fuel rocket engines, and sophisticated aerodynamics. Germany launched more than 3,000 V-2 rockets during the final months of the war, primarily against London and Antwerp. The attacks killed thousands of civilians but had little strategic impact. The rocket's true significance would emerge only after the war ended. When Allied forces captured the Mittelwerk factory complex in the Harz Mountains, they found a subterranean production facility where V-2 rockets had been assembled by concentration camp laborers under horrific conditions. American troops also discovered hundreds of partially completed rockets, tons of components, and crucial technical documentation. They immediately began shipping this material back to the United States, along with the engineers who had designed and built the weapons. Wernher von Braun and his core team of rocket scientists surrendered to American forces in May 1945. Within months, they were in the United States, working at Fort Bliss in Texas and White Sands Proving Ground in New Mexico. The Soviets, arriving at Peenemünde after the Americans, found less material but still managed to capture valuable equipment and recruit several hundred German rocket specialists. The impact of the V-2 on Cold War military technology cannot be overstated. The Soviet R-1 rocket, first tested in 1948, was essentially a reverse-engineered V-2. This led to the R-2, R-5, and eventually the R-7 Semyorka, the world's first intercontinental ballistic missile. The R-7 would also become the launch vehicle that placed Sputnik 1 into orbit in 1957, beginning the space age and shocking the United States into accelerating its own space program. American rocket development followed a parallel path. Von Braun and his team developed the Redstone rocket, a direct descendant of the V-2, which became the basis for the Jupiter-C launch vehicle. A Jupiter-C rocket launched America's first satellite, Explorer 1, into orbit in 1958. Von Braun would later design the Saturn V rocket that carried Apollo astronauts to the Moon. The strategic implications were profound. By the mid-1950s, both superpowers possessed nuclear-armed ballistic missiles capable of striking each other's territory. The V-2's descendants made nuclear deterrence possible, created the conditions for the space race, and established the technological framework for modern warfare. Every intercontinental ballistic missile, every satellite launch vehicle, every space exploration mission traces its lineage back to the work done at Peenemünde. Jet aircraft. The dawn of supersonic warfare. While the V-2 pointed toward the future of strategic warfare, Germany's jet aircraft programs revolutionized tactical aviation. The Messerschmitt Me 262, which entered service in 1944, was the world's first operational jet fighter. With a top speed exceeding 540 miles per hour, it could outrun any Allied piston-engine aircraft. Had it been deployed in sufficient numbers earlier in the war, the Me-262 might have seriously challenged Allied air superiority. The Me-262 embodied several technological advances that would shape post-war aviation. Its axial-flow turbojet engines, though unreliable, demonstrated a design approach that would become standard in jet propulsion. Its swept-wing design reduced drag at high speeds, a principle that would be adopted by virtually every supersonic aircraft developed during the Cold War. The aircraft also featured innovative ejection seats and pressurized cockpits, technologies that would become essential for high-altitude, high-speed flight. Germany developed other advanced aircraft that influenced Cold War aviation design. The Arado AR-234 was the world's first operational jet bomber. The Messerschmitt Me 163 Comet, a rocket-powered interceptor, achieved speeds exceeding 600 miles per hour but was too dangerous and impractical for widespread use. The Horten Ho 229 flying wing represented an early exploration of stealth design, with a shape intended to reduce radar detection. After the war, captured German jet aircraft and the engineers who designed them became prized possessions for both superpowers. The Soviets brought the entire production team of the Junkers Aircraft Company to the Soviet Union, where they worked on early Soviet jet designs. The Yakovlev Yak-15 and MiG-9, the Soviet Union's first jet fighters, incorporated German design principles and were developed with assistance from German engineers. The United States pursued a similar strategy. German aerodynamicists were recruited to work at American research facilities, including the National Advisory Committee for Aeronautics, the predecessor to NASA. Their expertise in high-speed flight, swept wings, and jet propulsion accelerated American aircraft development. The North American F-86 Sabre, which would prove its worth in combat against Soviet MiG-15s over Korea, featured swept wings based on German research. The knowledge transfer extended beyond specific aircraft designs. German research into supersonic flight, boundary layer control, and high-altitude aerodynamics provided both superpowers with a foundation for advancing aviation technology. Wind tunnel data collected at German research facilities saved years of experimental work. Theoretical papers written by German aerodynamicists became classified reading for American and Soviet engineers. U-boat technology. The silent service evolves. Germany's submarine warfare program produced innovations that fundamentally changed naval warfare during the Cold War. The Type XXI U-boat, which entered service in the final months of World War II, represented a revolutionary departure from earlier submarine designs. Unlike conventional submarines, which were essentially surface ships capable of diving for limited periods, the Type XXI was designed to operate submerged for extended periods. The Type XXI featured a streamlined hull design that reduced underwater drag, high-capacity batteries that extended submerged endurance, a snorkel system that allowed diesel engine operation while remaining underwater, and sophisticated sonar equipment. It could travel at 17 knots submerged, faster than most surface ships of the era. These capabilities made it nearly impossible to detect and track using existing anti-submarine warfare techniques. Both the United States and Soviet Union recognized the Type XXI's significance immediately. American naval officers studied captured Type XXI boats extensively, incorporating their design features into post-war submarine construction. The USS Tang-class submarines, commissioned in the early 1950s, were heavily influenced by German design principles. Soviet submarine development followed a similar trajectory, with captured Type XXI boats serving as templates for early Cold War Soviet submarines. Germany had also been developing closed-cycle propulsion systems that would allow submarines to operate without access to atmospheric oxygen. The Walter turbine, which used hydrogen peroxide as an oxidizer, powered several experimental submarines. While the system proved too dangerous and unreliable for widespread use, the concept of air-independent propulsion influenced subsequent submarine development programs in both superpowers. The impact extended to anti-submarine warfare as well. German passive sonar systems, acoustic torpedoes, and submarine detection methods were studied and refined by Cold War naval powers. The cat-and-mouse game between submarines and anti-submarine forces that characterized Cold War naval operations had its roots in the technological race that occurred in the Atlantic during World War II. Guided missiles and smart weapons. Germany's guided missile programs pioneered technologies that would become central to Cold War military strategy. The Henschel HS-293, an air-launched anti-ship missile, and the Fritz X guided bomb demonstrated that precision-guided munitions were feasible with 1940s technology. These weapons used radio command guidance, allowing an operator to steer the weapon toward its target while observing its flight path. The Wasserfall surface-to-air missile program represented an early attempt to create an effective air defense system against bomber formations. Though never deployed operationally, Wasserfall incorporated technologies that would appear in Cold War missile systems: supersonic speed, radio command guidance, and proximity fuses. American and Soviet surface-to-air missile designers studied Wasserfall extensively, incorporating its lessons into systems like the American Nike Ajax and Soviet S-25 Berkut. Germany had also experimented with wire-guided anti-tank missiles and infrared homing systems. The X-4 air-to-air missile used wire guidance, a technology that would be employed in anti-tank weapons throughout the Cold War. Research into infrared detection and tracking laid groundwork for heat-seeking missiles that would dominate air combat in subsequent decades. The sophisticated guidance and control systems developed for German missiles required advances in electronics, particularly in miniaturization and reliability. German electronic specialists became valuable assets in Cold War weapons programs, contributing expertise in radar, radio communications, and fire control systems. The integration of electronics with mechanical systems, essential for modern precision weapons, was pioneered in these German programs. The atomic question: Germany's nuclear research. Germany's nuclear research program during World War II remains a subject of historical debate, but its indirect influence on Cold War weapons development is undeniable. While Germany did not develop an atomic bomb, German physicists had made significant contributions to nuclear physics before and during the war. Many of these scientists emigrated before or during the conflict, with several playing crucial roles in the Manhattan Project. Those who remained in Germany continued nuclear research, though German efforts never achieved the scale or success of the Allied programs. When Allied forces captured German nuclear research facilities, they found uranium processing equipment, experimental reactors, and substantial documentation. The Soviet Union paid particular attention to Germany's nuclear program, bringing German nuclear scientists to the Soviet Union to assist with their own atomic bomb project. German expertise in metallurgy, chemistry, and industrial processes proved valuable to both superpowers' nuclear weapons programs. The precision manufacturing techniques developed for German weapons were applicable to the exacting tolerances required for nuclear weapons components. German chemical engineers contributed expertise in isotope separation and materials processing. More broadly, Germany's technological infrastructure and scientific establishment became assets to be divided between the superpowers. Research institutions, testing facilities, and industrial plants were either dismantled and shipped east or west, depending on which occupation zone they fell within. This physical transfer of scientific infrastructure accelerated both American and Soviet weapons development programs. Chemical weapons and nerve agents. One of the most disturbing aspects of Germany's secret weapons program was its development of nerve agents. German chemists discovered tabun, sarin, and soman, organophosphate compounds far more lethal than any previous chemical weapon. Germany manufactured these agents in quantity but, for reasons that remain unclear, never employed them in combat despite possessing the means to do so. Allied forces discovered large stockpiles of nerve agents and manufacturing facilities as they advanced into Germany. The existence of these weapons shocked Allied intelligence services, who had been unaware that Germany possessed such advanced chemical warfare capabilities. Both the United States and Soviet Union immediately began studying these compounds and developing their own nerve agent programs. The German chemical weapons program influenced Cold War military planning in several ways. The existence of such lethal compounds drove the development of protective equipment, detection systems, and countermeasures. Both superpowers developed their own nerve agents based on German research. The binary chemical weapon concept, where two less toxic compounds combine to form a lethal agent during munition delivery, originated in German research. The moral and strategic questions raised by nerve agents became part of Cold War military doctrine. The potential for mass casualties from chemical attacks influenced civil defense planning and military training throughout the Cold War period. International efforts to control and eventually ban chemical weapons were driven in part by the recognition of how devastating German nerve agents could be. Technology transfer and its long-term impact. The wholesale transfer of German military technology to the United States and Soviet Union created lasting effects that extended far beyond specific weapon systems. The recruitment of German scientists and engineers brought not just knowledge, but entire methodologies of research, development, and testing. German approaches to systems engineering, project management, and technical documentation influenced how both superpowers organized their military-industrial complexes. The competition to acquire German technology also established patterns of behavior that would characterize the Cold War. Both superpowers engaged in covert operations to deny each other access to German expertise. Intelligence services actively recruited German scientists who had initially gone to the other side. This contest in human intelligence gathering became a template for Cold War espionage operations. German engineers working in the United States and Soviet Union trained new generations of American and Soviet specialists. The transfer of knowledge occurred not just through formal technical reports, but through mentorship, collaboration, and the establishment of research traditions. By the 1960s, when most German specialists had retired or returned home, they had fundamentally shaped the technical cultures of both superpowers' military research establishments. The economic impact was also significant. Germany's war industries had developed advanced manufacturing techniques and quality control processes. The machinery, tooling, and industrial practices captured from German factories improved production capabilities in both the United States and Soviet Union. This industrial knowledge transfer contributed to the rapid expansion of military production during the early Cold War. Legacy of innovation and division. Nazi Germany's secret weapons programs cast a long shadow over the Cold War. The V-2 became the ancestor of intercontinental ballistic missiles that held the world in a balance of terror. German jet aircraft design principles shaped supersonic fighters and bombers. Submarine technology pioneered in U-boats evolved into nuclear-powered submarines carrying strategic weapons. Guided missiles became precision strike weapons capable of hitting targets thousands of miles away. The race to capture this technology also set the tone for superpower competition. The United States and Soviet Union learned that technological superiority could be achieved not just through original innovation, but through the acquisition and exploitation of others' work. This lesson influenced Cold War intelligence operations, technology transfer programs, and international scientific collaboration throughout the conflict. Moral complexities accompanied these technological gains. Many German scientists recruited by the United States and Soviet Union had been members of the Nazi Party. Some had directly participated in war crimes, particularly through the use of slave labor in weapons production. The decision to overlook these backgrounds in the interest of strategic advantage raised ethical questions that have never been fully resolved. The division of German technology between the superpowers also meant that innovations developed by a single nation became the foundation for opposing military forces. Engineers who had worked together in Germany found themselves on opposite sides of the Iron Curtain, applying their knowledge to weapons that might be used against each other. This strange brotherhood of adversaries was emblematic of the Cold War itself. Today, the influence of German wartime weapons programs remains visible in modern military technology. Intercontinental ballistic missiles, jet fighters, submarines, precision-guided munitions, and countless other systems trace their origins to work begun in Nazi Germany. The scientists and engineers who created these weapons could not have imagined how their innovations would shape the world for generations to come. The story of Nazi secret weaponry and the Cold War is ultimately a story about the dual nature of technology. The same knowledge that can advance human civilization can also create means of destruction. The same scientific expertise that launches spacecraft can design weapons of war. The lesson of this history is not just about the weapons themselves, but about how nations choose to use technological innovation and how the pursuit of military advantage shapes international relations for decades to come.